In the vast red landscape of Western Australia, something amazing happened. On June 21st, 2001, a train longer than any seen before or since began a journey across the desert. This was not just any train, it was a true giant of the railway world. The company BHP, a major player in the mining industry, decided to test the limits of what was possible with modern engineering. They assembled a train so long that it looked like a metal snake winding its way through the stark, beautiful scenery. This incredible machine was created to move a massive amount of iron ore, the rock from which we get iron, from a mine to the sea. The world watched as this experiment in size and power got underway. The numbers behind this record-breaking train are truly difficult to imagine. It was an astonishing 7.3 kilometers, about 4.5 miles, long from its first engine to its final wagon. To put that into perspective, if the front of the train was leaving a station, the back would still be several towns away. It was made up of 682 wagons, each one filled to the brim with heavy iron ore. The total weight of this colossal train was nearly 100,000 tons. That is heavier than many of the world's largest ships. It took 8 powerful locomotives to get this immense load moving along its 275-kilometer journey from the Yandi mine to Port Hedland. But why would a company like BHP build such a monstrously long train? The answer lies in simple economics and efficiency. The mining industry is all about moving huge quantities of material from one place to another. The more ore you can move in a single trip, the lower your costs become. A longer train means you need fewer train journeys to transport the same amount of ore. This saves a significant amount of money on fuel and also reduces the number of drivers and other staff needed to operate the railway line. For BHP, this experiment was a way to see if they could make their operations even more efficient and profitable. The journey itself was a slow and careful process. The train travelled from the inland mines deep in the Pilbara region out to the coast, where the ore would be loaded onto ships. This region is famous for its rich iron ore deposits, and heavy-duty railways are the arteries that keep the industry alive. The 275-kilometer trip was a major test for the railway tracks, the wagons, and the locomotives themselves. Every meter of the journey was monitored to ensure that this giant train could handle the pressure. It was a bold statement of industrial power, showing how technology could overcome the challenges of distance and scale in one of the world's most remote environments. Moving a train that weighs almost 100,000 tons is not a simple task. You cannot just put all the power at the front. If you did, the couplings connecting the wagons would snap under the immense strain. The front wagons would be pulled with incredible force, while the wagons at the back would not even have started moving. To solve this problem, engineers use a clever system called distributed power. This means the locomotives, the engines that provide the power, are not all grouped together at the head of the train. Instead, they are placed at different points along its entire length. This distribution of power is the secret to making super long trains work safely. For the 2001 record-breaking train, the 8 locomotives were arranged in a specific pattern. There were locomotives at the front, in the middle, and near the back. This setup ensures that the pushing and pulling forces are spread out evenly. The locomotives in the middle of the train help to push the wagons in front of them and pull the wagons behind them. This dramatically reduces the stress on the couplings between each wagon, preventing them from breaking and causing a major accident. It's like having a team of people pushing a very heavy object from different sides, rather than one person trying to pull it all by themselves. The locomotives communicate with each other using advanced radio technology. The driver in the lead locomotive controls all the engines simultaneously. When the driver accelerates, a signal is sent to every locomotive along the 7.3-kilometer length of the train, telling them all to apply power at the same time. The same thing happens when the brakes are applied. This synchronized control is crucial for smooth operation. It ensures that one part of the train does not speed up or slow down before another, which could cause the wagons to bunch up or stretch apart dangerously. It is a high-tech ballet of power and precision. Thanks to distributed power, mining companies can run incredibly long and heavy trains every single day. While the 7.3-kilometer train was a one-off experiment, the technology it tested is now standard practice in the industry. It allows companies like BHP to maximize the amount of ore they can carry in a single trip, making their operations more efficient and cost-effective. The system has proven to be reliable and safe, transforming the way heavy materials are transported by rail. It turned the idea of a super long train from a risky dream into a practical reality for modern mining. The world record set in 2001 was a special event, and it remains unbroken for a very good reason. The 7.3-kilometer train was an experiment, not a new standard for daily operations. BHP wanted to understand the absolute limits of their equipment and infrastructure. They learned valuable lessons about the stresses on the track, the performance of the locomotives, and the behavior of such a long train. The experiment was a huge success from a technical point of view. It proved that it could be done. However, running a train of that extreme length created practical challenges that made it unsuitable for regular use. One of the biggest issues with such a long train is its lack of flexibility. A railway network is a busy place, and a 7.3-kilometer train takes up a massive amount of space. It can block junctions and crossing points for a very long time, which can disrupt the schedules of other trains on the line. Imagine waiting at a railway crossing for a train that takes more than 10 minutes to pass. For a company running a complex network with many trains moving back and forth, this can create logistical nightmares. The record-breaking train showed that while bigger can be better, there is a point where it becomes impractical. Because of these lessons, BHP and other mining companies chose not to make 7-kilometer trains a regular occurrence. Instead, they found a more optimal length that balanced efficiency with practicality. Today, the typical iron ore trains in the Pilbara region are still incredibly impressive, but they are shorter. They are usually between 2.5 and 3 kilometers long, consisting of around 260 wagons and pulled by 2 or 3 locomotives using the same distributed power technology. This length has become the sweet spot, long enough to be highly efficient but short enough to be managed effectively within the existing rail network. The 2001 record, therefore, stands as a monument to engineering ambition. It was a test that pushed the boundaries and provided crucial data that helped shape the future of the industry. It wasn't a failure because it wasn't repeated. It was a success because of what was learned. It taught engineers the maximum capacity of their systems and helped them find the perfect balance for their daily operations. The legacy of that giant train is not in its unbroken record, but in the thousands of slightly shorter, highly optimized super trains that run safely and efficiently across Australia every single day. The world of railway technology is always moving forward, and the future of heavy freight trains looks even more advanced. One of the biggest goals for the industry is to reduce its environmental impact. While trains are already a more efficient way to move goods than trucks, companies are exploring ways to make them even greener. This includes developing locomotives that run on cleaner fuels, such as batteries or hydrogen. Imagine these powerful trains pulling thousands of tons of ore across the desert with zero harmful emissions. This is the direction the industry is heading. Another major trend is the increasing use of automation. Just as distributed power revolutionized how long trains could be, artificial intelligence and autonomous systems are set to change how they are operated. Companies are already testing trains that can drive themselves. These automated trains can be programmed to run at the most fuel-efficient speeds and can operate 24 hours a day without needing to change drivers. This not only improves efficiency and safety by reducing the chance of human error, but it also allows the entire rail network to be managed more effectively by a central computer system. In the future, we may see trains that are not only automated but also smart. They will be equipped with sensors that constantly monitor the health of the engine, the wagons, and the track itself. If a problem is detected, the train could report it automatically or even slow down to prevent an accident. This constant stream of data will help companies maintain their equipment better and predict when repairs are needed, making the entire system safer and more reliable. The railway will become a connected, intelligent network where every part works together seamlessly. The spirit of innovation that led to the record-breaking train in 2001 is still very much alive. Engineers continue to ask, how can we make this better, faster, safer, and more efficient? Whether it is through cleaner energy, smarter automation, or new ways of managing complex rail networks, the freight trains of tomorrow will be technological marvels. The journey from that 7.3-kilometer giant to the automated zero-emission trains of the future shows that the railway industry is always on the move, pushing the limits of what is possible.